Okay, so our next speaker is Chris Soteros, who's going to be talking to us about entanglements and lattice polygons in tubes. Give you a second to set up, Chris. Okay, that's looking good. Thanks. Okay, take it away, Chris. I think you're...
Okay, thank you very much.
Yep, go ahead.
Okay, thank you very much. Acknowledge that I live and work on Treaty 6 territory in the homeland of the Métis, and I pay my respects to the First Nations and Métis ancestors of this place and reaffirm our relationship with one another. And since I'm coming from Saskatoon today, I noticed that I'm probably the northernmost speaker. I think we're at just above 52 latitude or parallel, and I think England is, or at least London, England is just above the 51st. And thank you to the organizers for giving me an opportunity to remember Richard. Oh dear. Alrighty, I have technical problems. Okay, I'm going to start again. Okay. So I think I met Richard first back in the early 90s at a number of the critical phenomena and polymer physics conferences that were held in Southern Ontario. I did a postdoc with Stu Whittington, and that's where I was introduced to lattice models of polymers. And one of the things I shared interest with Richard was modeling collapse phase transition, and also Monte Carlo methods. And I was really impressed that Richard and Alex were willing to come to Saskatoon back in '94 for an informal workshop that I had on Monte Carlo simulation. And then I really benefited a lot by the next year, Richard hosting me for my first sabbatical in Melbourne. And Mireille already talked about how exciting that time was. I met Mireille there as well as others. And from Richard, we worked on a problem related to Monte Carlo of self-avoiding walks, and it resulted in a paper. But also I learned a lot about the natural beauty of Australia and to appreciate it. And I, like Mireille, remember very well seeing the koalas in the wild. And I also appreciated the hospitality of Rachel, and also meeting Sam and Joe, who were quite young at that time. The other thing that I sort of was jealous of Richard was he was working on solvable problems. And to that point, I really hadn't, everything was, we could prove some things, but there was always these unanswered questions. And so I was looking for a problem that was more solvable. And well, didn't end up, as you'll see today, that still ended up having lots of unsolvable parts. But later in that same sabbatical, I learned how to prove a pattern theorem for polygons in lattice tubes based on some work by Alman Jensen on transfer matrices for self-avoiding walks. I think I learned about that paper by Alman Jensen from Neil Madras. So, and over the years, Richard has provided great support to me and my career, and he's invited me to conferences, but also attended conferences, and there was always very useful discussions and talks at conferences, and as well as providing advice and listening to me gripe about academic politics. So this picture on the left you've seen before, that's from my first sabbatical in Melbourne. And this last picture, I think is the last time I met Richard in person, and that was in 2015 at the Canada conference in Saskatoon. All right, so I'm going to talk about polygons in tubes, lattice tubes, so sublattices of the simple cubic lattice. And I've been I started working on those actually way back when I did my postdoc with Stu Whittington, but there's been recent reinterest in these models because of recent experimental results involving DNA in nanochannels and nanopores, and where these experiments can be used to sense whether the DNA is knotted or not, and then also even what type of knot is in the DNA. So I've been using these lattice models and tubes to model roughly, simply DNA in a nanochannel. And there's now the experiments are definitely non-equilibrium. The models I'm looking at are definitely equilibrium, but there's a lot of open questions that we can explore using the equilibrium model. So for example, what are the characteristics of the knots and links at equilibrium? And how is it affected by the confinement? And so there was the typical size of the knotted or linked part relative to the length of the polymer. And this leads to many interesting mathematical questions. For example, how does one even measure the size of the knot or link region? And then are the knot or links localized, and to what extent? Thereby localized, we mean if you've got the size of the polymer or the polygon is length n, then if you can determine a way to measure the knotted region and say that size is m, if the ratio m over n goes to 0 as n goes to infinity, we say the knot is localized. And also another question is, it's been observed in these experiments that or at least in simulations of the experiments, that there could be two different ways that the knot can occur in the polymers. And I'll talk a bit more about that later. And so is there something that mathematical models can say about whether different modes of knots are more likely than others? All right, and so of course, this is simplified model. So even though DNA is a double helix, I'm going to just model the backbone of the DNA by a walk or in a polygon on the lattice. And I don't think I have to convince people here that this can be a reasonable model. Outside the tube, so without confinement, people have looked at the probability of knotting. And so there we let Pn be the number of distinct n-edge self-avoiding polygons in the simple cubic lattice, and Pn of phi, but also I'll use 0, 1 to denote the unknot. So Pn 0, 1 will be the number of distinct unknotted self-avoiding polygons, Pnk the number of a specific knot type k. And then back in 1988, Sumners and Whittington proved that the probability of knotting, so the 1 minus the probability of the unknot, goes to 1 exponentially. And there they used a pattern theorem to show that a tight trefoil pattern has to occur frequently in any polygon. And so also with Sumners and Whittington, we showed that the probability of any fixed knot type goes to 0 as n goes to infinity. And then based on, so I don't know, let me see, okay. So based on some numerical work back in 98, Orlandini et al., they conjectured that these counts of polygons with fixed knot type should go roughly like constant times n to a power times something that grows exponentially at the same rate as unknotted polygons. And the exponent in the power was thought to go up by 1 for each prime knot factor in the knot's decomposition. And so roughly the hand waving argument was that a typical large trefoil polygon, say, looks mostly like an unknot, but with the trefoil part being small within it. And so if I'm counting them, it's roughly like I have n places along this polygon of length n to put in this little small trefoil pattern. And so there's lots of numerical evidence to support this, but other than it can be shown that the exponential growth rate for the unknot is strictly less than that for all polygons, but there's not even a proof for the existence of the exponential growth rate for any other fixed knot type K. And so aside from being motivated by looking at polymers in confinement, was also interested in whether we can say anything about polygons in tubes, and with fixed knot types, whether we can learn anything about the scaling form in that case. So the advantage of I'm going to look at polygons in a tube where we've restricted the height in this direction will be some value m will be limited, and in this direction, this distance will also be fixed. But we'll let the polygons grow in the x direction. And we'll look at the simplest case where I'm going to call each, say that each polygon of the same size is equally likely. And we count polygons. We assume all polygons have a vertex in the leftmost plane being the plane x equals 0 and grows to the right. So the main tool that I've been using to study self-avoiding polygons is transfer matrices. And so basically that's because essentially, because we're in a tube and you're only letting things grow in one dimension, it's essentially a one-dimensional problem. And so you can think of a self-avoiding polygon as a sequence of connected one patterns that grow in the x direction. And so there'll be some starting configuration on the left of the polygon, and then this in red is a possible, what we call a one pattern, and it can happen on such a slice, and then the next one will be, it has to be followed by a one pattern that can connect to the previous one, and so on. And so basically, and then there's a pattern that ends the polygon. So basically, I can think of a polygon in a tube as a word made up of letters, where the letters are these one patterns that can occur on a slice. And but we have restrictions. We only allow certain letters to follow other letters if they can connect together properly to make a polygon. And so you can get a transfer matrix like this, where each row and column corresponds to one of these letters, one of these possible configurations on a slice. And if this pattern can follow this pattern, then we put a non-zero entry in the matrix, and we put in a factor, say x to the cube, something that takes into account what we want to keep track of eventually in our generating function or partition function. And so the advantage is then that we can get a grand canonical partition function, which associated with the count, say here I've got it, PTNS is the number of polygons in the tube with n edges, and span S. So the span is the distance in the x direction between the leftmost plane and the rightmost plane. And then this generating function can be written in terms of, so my transfer matrix is g of x. The generating function can be written in terms of powers of the transfer matrix. I'm taking ij coefficients, and this is proportional to 1 over the determinant of I minus y times the transfer matrix. And so because of this, we can relate the eigenvalue of the transfer matrix to the radius of convergence of the generating function, which in turn gives us is related to the free energy for these counts, or in the case where we're looking at the equally likely case, it'll give us exponential growth rate of the number of polygons. And eigenvectors also associated with different letters or those different one patterns can also tell us about the frequency of occurrence of those one patterns. And so in that sense, this, if you have the transfer matrix, this problem is completely solved. But it's completely solved if you're only interested in knowing about the polygon counts. But if you want to know about knot types and how frequently you have an unknot, unfortunately, you can't tell whether you have an unknot just by looking at the slices that make up the polygon. You really need to construct the whole polygon. It's a global property, the knot type. And we have constructed, this is from Jeremy Ng's PhD thesis, we have constructed a number of the transfer matrices for polygons up to say 3x2 or 5x1 is the largest we got to. We looked at separately what we call Hamiltonian self-avoiding polygons. Those are polygons that occupy every vertex between their leftmost plane and rightmost plane. And we also looked at, and the advantage of those is we expect them to have the same asymptotic properties in terms of, say, the scaling of the probability of the knot type, but we see more knots in the Hamiltonian self-avoiding polygons. Okay, so what I wanted to highlight is a new result that where we actually can prove this scaling form that's conjectured for the whole lattice. We can actually prove it in the special case of the smallest tube that admits knotting, so the 2x1 tube. And for those who might have heard me talk about this before, previous versions of this, we didn't have an upper bound proof for all possible knot or non-split links, but now we do. So in the past year, my topologist collaborators have come up with an argument that works for all possible knots and non-split links that fit into a 2x1 tube. Okay, so rather than sort of go through all the details of the statement, let me just sort of say what the statement says. It says that if we start out with we have an upper bound argument and we have a lower bound argument, the two arguments use quite different ideas. So the lower bound, we start out with an unknot, and we have proved a pattern theorem for unknot polygons in the 2x1 tube. Basically, that says there's a density of places where we can insert any other pattern of a certain type. And so then we can turn an unknot polygon into any fixed knot or link type that can fit in the 2x1 tube by inserting patterns associated with the prime factors of that knot or non-split link. And so I can find two places to insert a trefoil pattern and get this connected sum of two trefoils, or I can find a place to insert a Hopf-link pattern and I can get a Hopf-link, or I could get connected sums of Hopf-links. So the lower bound argument comes from proving a pattern theorem, and that relies on the transfer matrix arguments. And then the upper bound involves new knot theory, where my knot theory colleagues have used the fact that in the 2x1 tube, we know these knots or links that can occur are connected sums of two bridge knots or links. And so because of that, they can use the results about four-plat diagrams. So two bridge knots and links are also called four-plats. And so they have a four-plat diagram associated with that. And the properties of the braids that make up these four-plats, you can find a four braid, given any of the fixed knot or link, you can find a four braid to insert that the size of the four braid only depends on the crossing number of the original knot or link, and not the size of the polygon that contains it. And you can find a place where to insert this braid, and you can unknot it. And you get a factor of n choose FL because there could be up to that many different initial configurations that lead to the same unknot configuration. And so because of this argument, we can actually get precise bounds that relate unknot polygons to knotted polygons with a fixed knot or link type. And so the roughly speaking, this is what the upper bound argument is. So we start out with I think this is a trefoil in, or no, it's a knot anyway. Might be a 6 crossing knot. I've forgotten now. In a tube, and we get from that a shifted diagram, and from the shifted diagram, you can get a 4-plat diagram, and then there's an associated minimal diagram for that link. From that a 4 braid, a location can be determined where to insert this 4 braid, and in the original thing, and we can get a lattice version of that 4 braid, and just inserting that in the right place turns the original lattice embedding of the link into the unknot. And so this is all using new knot theory results. And then, sorry, for the lower bound, that's here. So here we start with an unknot polygon, which has a lot of what we call 2 sections. So 2 section will be at a half integer plane where you've only got 2 edges going across. And so we can show that there's a density of these places, and any place where you have one of these 2 sections, we can insert what we call a connected sum pattern. So a pattern that ends and starts and ends with a 2 section, and we can convert this unknotted polygon into a polygon of any knot or non-split link type. And so I'm running short. So this is just summarizing what I said. If I'd had more time, I would have explained more about what the lower bound argument is, because that involves the lattice combinatorics. Basically, we can use the transfer matrix, and this work was done with Nick Beaton, and we can use the transfer matrix that we've constructed to get an upper bound on polygons without 2 sections, and use that to show that unknotted polygons without 2 sections have to be rare compared to unknotted polygons. And then we can use arguments to show that there must be a density of 2 sections in these unknotted polygons. And then once you have there's a density of 2 sections, you can also get a more general pattern theorem for unknotted polygons, because we have a way to insert patterns into the unknot. And so we can use Neil Madras's general pattern theorem arguments. If once you have a way to insert patterns, you can get a general pattern theorem for unknotted polygons. Okay, and so just quickly, so the problem though, so the lower bound argument, we may be able to extend to 3 by 1 because we have the transfer matrix, and we may be able to get the numbers to work out. But the upper bound argument, the knot theory is not there for the upper bound argument. So unfortunately, going to higher tube size is problematic for this. So some other things we've looked at is we can develop a Monte Carlo method based on the transfer matrix for studying these polygons and other embeddings in tubes. And we've identified 2 different ways, say a knot can occur either as what we call non-local or local, or some call it 2 filament or filament. So the local, the knotted part is just in 1 string, whereas in what we call non-local, it takes both strings apart. And what we showed for small tube sizes, our numerical evidence shows that the non-local patterns seem to be more likely but and we can also look at linking, but we haven't done this numerically, but there are sort of two modes that a link could occur. And to some extent, Stu and Enzo have a recent paper where they've looked numerically, not in the tube, but in general links, and found that this one type of mode is more likely than the other. And maybe the final word I'll say is, so while for small tubes, we saw that those non-local patterns were more likely, as we increase the tube size a little bit, the probability, the non-local ones were still more likely than the local, but the difference started to decrease, so that the difference in those two probabilities may end up being closer to the same in the end. So I'll stop there.
Okay.
Thank you.
Thanks for an excellent talk. I'll start with asking if there are any online people who'd like to ask a question.
Nathan, can I ask one?
Yes, please do, Stu.
Hi, Chris.
Hi.
So did you say—
Nice to see you.
Nice to see you too. I haven't seen you for 2 years. Did you say that your upper bound in these small tubes works for connect sums of two bridge knots?
Yes, yes.
So you have to add this special or these particular 4 braids in for each of the components in the connect sum?
That's right. So it turns out in the 2x1 tube, we know that we can isolate the factors. And so then we can find the places to insert. So that's one of the problems with 3x1. You no longer know anymore that you can isolate things. So even if we only had 2 bridge or connected sum of 2 bridge and 3x1, we don't know anymore in 3x1 that we can sort of separate the factors. Things could be overlapping. Yeah.
Yeah, okay, I see. I've got a sort of an auxiliary question. So if you're in a bigger tube, and if you knew that the knot was a 2 bridge knot, could you still play the same game?
No, that's what I'm saying. So in 3x1 already, we don't know that.
No, that's if you have a connect sum of 2 bridge knots. I'm talking about if you had a single 2 bridge knot.
No, because we rely a lot here on the fact that we can reduce things to just having 4 strings going across. So like whenever you have 6 strings, basically nothing can happen. So then we can get rid of all the 6 string things. And so we know we only have to look at 4 strings going across. And so the problem is when you go up to one size bigger, you don't have that anymore. So I think that is part of the problem.
Yeah, okay, I see.
Yeah,
Thank you very much.
So there's lots of problems, unfortunately.
Thanks.
Are there any further questions online? Okay, I'll hand over to the audience. Any questions from the audience? Yeah? No? Okay, so in the interest of time, because we're running just a touch over, I think we'll leave it there, but thanks very much for a really interesting talk, Chris.